Good morning, everybody. Anybody hearing me?
Yep.
Yes.
Okay, good. This is the third day of our carbon isotopes workshop. The focus is on development of reference materials. This is continuing a conversation that we started yesterday, mid-morning for me, afternoon for you, I guess. We talked a little bit about calibration yesterday, and today the discussion is going to be focused on reference materials that we can use to bring our observations onto the same scale, although I acknowledge that there are some calibration issues that are still outstanding, and we're going to have discussion time later to cover those. Just to summarize what was presented yesterday, Anne noted that as far as radiocarbon goes, there haven't been that many inter-laboratory comparisons. NOSAMS has essentially been the US lab producing all of the GOSHIP and CLIVAR measurements and the WOS measurements. And in the early stages of WOS, there was some comparison with the traditional technique of collecting a 50-gallon sample and counting. There was good agreement in those comparisons that were performed along P6, P19, and P17. Bob talked a little bit about whether or not he was happy to see those Gerard barrels go over the side during WOS P10. Bob, I went and read the cruise report. Actually, 2 of the barrels survived, so if we need them, we're going to deploy you.
Yes, that's correct. We only lost 7 out of the 9 that were hung.
So for radiocarbon, for modern techniques, there was a recent comparison between ETH Zurich. This was presented by Maxi Castrillejo, if I got that right. And the agreement was plus or minus, this was about 14 samples. NOSAMS collects in 500 cc glass bottles, and ETH Zurich actually collects samples in bags and freezes them. Those bags were frozen for 14 months before they were thawed and transferred to bottles and analyzed. And ETH Zurich agreed to then plus or minus, well, was lower by 1.5 per mil approximately, with excellent precision actually. At that point, Heather Graven weighed in because she was just delighted at how good this agreement was. It was much better than she had found in an earlier comparison between NOSAMS and a Scottish facility. One thing that seems to be missing from this meeting is a comparison of the Japanese AMS radiocarbon program with NOSAMS. So that's an intercomparison one could argue still needs to be done. For C13, we saw some results from Anne showing that the new NOSAMS technique agreed with the more traditional technique from the University of Washington. And that's just from stations of opportunity that are at approximately the same season, year, and location. Anne covered an informal interlab comparison, approximately 6 labs. They found that everybody nails the number when you're just looking at the CO2 gas replicates. Everybody gets the same number. But when we start talking about actually stripping or extracting a water sample and measuring the del C13 of the DIC, there can be significant disagreements up to 0.1 per mil. And that is one of the foci, can I say that, of today's meeting, is how to bring those labs that can be very precise onto the same scale so that we can combine our data sets as one sort of climate product. Anne also presented an interlaboratory comparison of about 10 labs, I think it was 9, but then Kalina Godospinova, is that right? Added NOSAMS to that comparison. And although there were still differences amongst the labs up to 0.1 per mil, that study showed that when you normalize the labs to a common reference value, the del C13 measurements are, for all the labs, are brought to within the global ocean observing system criteria necessary, which is about plus or minus 0.005 per mil. So talking about future interlaboratory comparisons, one could argue that for the del C13 of DIC, the comparison has already been done. I put down the caveat here that I don't know if all of the labs that participated in the Cheng et al. Comparison are in this group today. And I don't know which labs are missing. So if you are missing, please indicate in that if you were missing from that study and would like to participate in a future C13 intercomparison, please put that in the chat. That's my red. That's to remind me to ask you to do that. For radiocarbon, I am of the opinion that a formal interlaboratory comparison is needed in the future. We had a poll on the website, and about 13 labs returned, well, 13 labs voted. The questions were about what kind of reference materials you happen to be using at the present time. It looks like most labs use solid reference materials. 2 or 3 of them use solid reference materials that they then dissolve to make a liquid reference material. And 3 labs used sort of internally prepared proprietary seawater standards. 1 lab uses a Dixon DIC standard, which we'll hear more about today. 9 labs noted that they would use a dissolved CRM for carbon CRM certified reference material. 9 labs noted that they would make use of a dissolved CRM for carbon isotopes. I put a caveat at the bottom, and it's a note from yesterday's discussion, and that is that in the seawater, I look at this as a blue water oceanographer, and we're talking about a C13 range of 2 to minus 0.5 per mil. So a certified reference material that is approximately 1 per mil that brings all the labs onto the same scale is of great utility for me. But there are many, many groups that encounter a larger dynamic range than just a per mil and a half and have additional needs. So I don't want to steer the conversation entirely in the direction of what Rolf Sonnerup wants. But anyway, that's just what I thought I'd note. This is the outline for today. After a long-winded introduction, we're going to hear about how Weijun Kai is using standards for a non-isotope ratio mass spec method. It's a cavity ring down laser absorption device. And then we are going to have, this is really great. We have Andrew Dickson from Scripps, who has been preparing DIC standards, dissolved inorganic carbon concentration standards for the ocean community for quite a while. And we're going to have a presentation from Regina Eastley from NIST, National Institute of Standards and Technology, helping advise us on how to move forward with efforts to have uniform standards for this community. At 11, approximately, we're going to have some general group discussion about what interlaboratory comparisons might still be needed. I hope to limit that to only 15 minutes or so that we can have a roundtable discussion. We have sort of a panel leading the discussion about CRM development going forward. We'll have a break at noon, and then we'll have breakout group discussions after, this should say 12:30, everybody. Sorry, I can't eat that quickly. We'll have a breakout discussion at 12:30, and we're hoping to break the groups into seawater C13, seawater radiocarbon, and freshwater groundwater groups, so that people can focus what their reference material needs are going to be going forward. And then we will have a wrap-up session at the very end of the day. I lost my screen, everybody. Can you see anything?
I think you went to the last slide. So if you go back one. There you go.
I was bragging about being a techno wizard this morning. Okay, so at 1:15 we'll wrap up with a summary discussion. Okay, that's it. Oh, I should introduce the next speaker. Our next speaker is a professor at University of Delaware. His name is Weijun Kai, and he's going to talk about standardizing or calibrating a laser ring down absorption device.
Thank you, Rolf. Could you unshare? Okay.
How's that?
Oh, you are still. Oh, okay, got it. Yeah. So I just used my Monday's talk and focus on how we do the standardization and with a Piccolo-based system, and also drawing off my thoughts on the reference material part. And thanks for the introduction and for the opportunity to speak on the Piccolo-based, because you guys are all more familiar with the isotope ratio mass spec. So this is a little different, but I want to start with what we everyone eager to jump in yesterday on the 3 different approaches for standardization, and I promise to get back to that. Okay, liquid, gases, and base, and solid. So since Piccolo based is a little different with the IRMS, so I'd like to just briefly mention how we do that. So our system really have 3 different parts. One is CO2-free compressed air through a mass flow controller, deliver about 60 milliliter per minute to bubble the reactor and extract this CO2 in seawater or whatever sample that is, and through a condenser and go to Picaro. And so this is the second part. And another part is use a precision digital pump to deliver both standard, liquid standard, and samples. So we get both DIC under the integration curve and the average of with the DIC reading. So the procedure is, what we do is first draw acid into the syringe and then draw sample on top of that. And then once you build a stable baseline, we just push this into the reactor and going through that. So this is what we do with standardization. We prepare actually 2 bags with sodium bicarbonate, and actually we went to a lot of stores to buy baking soda and tested them. And we got one is like -1, another about -3, and then some more negative because we also do upstream work to -10. So we have a stable isotope lab, UD measure the delta C 13 value, but to be sure, we also sampling these back from time to time, and each time when we change a new bag or change a bottle of gas, we actually sample them, send to UC Davis stable isotope facility for analysis. And we have 2 Piccolo-based systems. The older one actually agrees with whatever come back from UC Davis, very close. The new one we bought it just before pandemic, always have a little bit off, and we still need to get them to calibrate for us. So we also are, because of that drifting of the new system, we feel needs to actually use a bottle of air gas from NOAA's atmospheric standard lab. One is about 7.9-ish, and another is -20. And they provide a very good check of the stability of the system. However, there's also issues. So we try to work with them, see if they can prepare gas standard more positive. They say that's possible, but right now with all the fire in the West Coast, they couldn't do that. So we'll wait a few more months to get acquire that. But they do say they can provide 0.02 per mil to that precision. So that is something we really love to get that. And yesterday, Monday, I already mentioned, this is what we did during the recent cruise to the Gulf of Mexico. With that 2 bag of standard, we can get an overall variation over 40 days within 0.5 per mil. But if we use that as a standard, then we should expect our sample analysis, to get a result a little better than that. Now, each point is a repeat of 3 or 4 injection, and that alone itself is within 0.05 as well. So we got stable, and then we also actually got a CRM, thanks to Andrew for providing this 195, most recent one. And because it's very hard to get a CRM, we only opened 5 bottles, and that's again is within 0.05, including this power failure and restart. So we are quite happy with that. And another thing I want to mention is we do duplicate water bottles every 10 samples. That also repeat well. Now, this CRM, we didn't calibrate. This is just the raw data off the machine, 0.78 is the average. And that actually agrees with the CRM 157 that in that chain lab, not far away, 0.82 they got. So I think there's maybe a hope that the CRM Andrew currently prepared seems a relatively stable isotope value with C13, and we actually measured the various different batch. They change a little bit, but overall, this seems promising. So I want to mention some problem and challenges with the Piccolo-based one. Actually, Piccolo is sensitive to the carrier gas composition. So far, the compressed air we got from air gas actually is not real air, it's synthetic air, nitrogen balanced by oxygen or the other way. So we used our, we have a mass spec, for oxygen argon, and there's also nitrogen. So we measure that ratio, find that each bottle has a little bit of variation. They lead to 0.3 per mil changes. So that forces us to rely on that liquid standard so far. So we very much want to either get rid of this, use like compressed air, for example, if we have to do that long-term standard ourselves, because we find it's a pain to send our subsample to UC Davis. So we very much want to acquire that more positive data C13 from Boulder, Colorado, NOAA's atmospheric lab, and then we'll test the carrier gas. But one thing very encouraging to me this time is when I hear yesterday we talk about the standards. So the liquid, I'm fully for seawater CRM, as I said, maybe they are quite stable, at least within that batch. You see that 5 bottles we open over 40 days, get a very good result. And when we talk about a gas, maybe you guys with the IRMS or talk about pure gas, I suppose. But for me, if I can acquire 1,500 to 1,000 ppm air-based, I'm sorry, CO2, air-based CO2 gas from a calibrated lab from NOAA standard, that actually I could calibrate my Picaro directly, and we already test there's no fractionation, whether it goes through the gas stripping reactor or directly go to Picaro. So that's a good sign. Now, I just want to mention this about a solid that Bob Key mentioned yesterday, that during the early day of CRM, before CRM age, that for DIC analysis, there is this up to 20 micromole difference in the DIC data. So using salt prepare from solid, I understand that, but I just urge that our community not give up the solid yet, because I feel there is a real difference between DIC and delta C13, because here you don't need the absolute concentration. If whatever CO2 coming out, as long as that's 100% from that sodium bicarbonate or calcite, for primary standard, then it will be probably okay. So we should have an open mind with the solid-based approach. So I think we need, all 3 and at this stage for comparison. And if I could have just 1 minute, I want to show for some of the people don't not familiar with ocean data C13, there's one figure from March 2020. We went to this cruise, actually A13 at this area. We went out only for 7 days, then we were ordered to come back to US. So you can see this, that DIC, we compare with 10 years ago, 2020 compared with 2010. There's about a 15 micromole DIC increase. But the delta C13, the decrease because of Susi effect is very significant, 0.3 per mil difference. Although the surface to the, the natural change, so it's like 0.9. So 0.3 out of 0.9 per mil, but the DIC 15 out of 150. So I think if we could do this delta C13 well and at sea, and there is this is really will be a powerful tool for constraint anthropogenic CO2 uptake and for study carbon cycle in general. Thank you for the opportunity to talk. I'm done.
Hi, Wei-Jin, could you sort of go briefly over how the Picaro measures the isotopes and how you calibrate them?
Yes, so the Piccolo really, it's a laser tuned method. So internally, Piccolo really based on measure delta C13, measure C13 reference to C12. So when CO2 concentration is really low, below 100, the C13 data are no good, very noisy. So they actually recommended a cutoff that, for 400 ppm. Anything below that actually will not be accurate. They guarantee if you are above 400 ppm, it will be 0.1 per mil. But the way test in the lab actually, as long as you are above 100, you are okay. But we adopt their recommendation. On the other hand, because we use the area of DIC as a weight, so although so most of the high concentration one dominate the delta C13, and now we actually also reduce the pumping speed adding this. So we have a much larger, broader peak that actually improves the accuracy, because this way you will dominate the delta C13 by most of the high CO2 data, and the Piccolo 2131 actually guarantees 0.05 per mil when CO2 is above 1000 ppm. I don't know if that answers a little bit of this.
Wei-Jin?
Yes.
So it's measuring the absorption of a tuned laser at 2 different frequencies, one for C12 CO2 and one for C13 CO2. Is that what it's doing?
Correct. But internally, that C13 is referenced to C12. So
okay.
And I don't think they do that C13 as frequent as C12. So the data, when we take as per second frequency, is really interpreted internally, I think. And the thing, if anyone want to use that very keen one, we don't really know. It's actually sensitive to the composition of carrier gas. So that is something we really need to be careful for, yeah. So for example, when you set up an underway system, if you are going through a hypoxia area, that may affect a little bit, but I don't really think so that people warned because of water. But this, your carrier gas doesn't change, then it should be fine. Yeah, so one other advantage is you could really set this as underway and continuously measure that pumping water up.
Adam Subas has his hand up.
Pardon me?
Hey, let me turn
Adam,
the video
yeah.
on here. Hey, Wei-Jin, yeah, nice talk.
Thank you.
Great to see what you're doing with the system. I just a couple of points about the Picaro in case anyone else is interested in the system. We actually have had pretty good success running the system with nitrogen, so ultra pure nitrogen as a carrier gas. I know that's not, historically, that hasn't been recommended based on, I think, an old paper by Doug Wallace, but it's actually pretty stable. And maybe that's one way to get away from this, slight O2N2 mixture problem. The other thing to point out for groundwater folks, the Picaro measurement is also pretty sensitive to methane concentrations and sulfide concentration. So if you're doing groundwaters or pore waters, you just have to be a little bit careful with those two other volatile gases.
Well, thank you, Adam. I think that's really good news. I know people in Xiamen University in China, they actually calibrated their Piccolo against nitrogen, and they use pure nitrogen, yeah. And that probably is a good approach. And really here, you don't need to, well, if you initially buy the system with Piccolo calibrate against nitrogen, that probably will be even better, yeah.
Yeah, exactly. And they actually they suggest that you use nitrogen if you're hooking up a combustion module and doing combustion of sediments or organic carbon samples for Delta C13. So that is an option that you can get from that.
Thank you.
Mark? Yeah.
Yeah, thank you for an interesting presentation. I was just wondering if you could comment on the scatter in your SUS effect profile diagram, the scatter around the dark line. I have to admit that because during pandemic and my postdoc was not able to come here. Actually, he went home for Chinese New Year and couldn't return. So we hastily sent a technician there who was not familiar with the system. So I think the standard deviation, there is some issue, but this is large scatter is because we actually form multiple stations. Okay, so there are natural variability, but because our precision probably 0.08 per mil rather than anything better we did. So actually we plot all 8 stations together. I just want to have some idea, how overall that region works. Thank you. Okay, thank you.
All right,
Very interesting.
Wei Jun, thank you.
Thank you.
Actually, there was one question in the chat, Rolf.
From Jennifer Walker. Wei Jun, how long is the interaction of the sample water with the acid inside the syringe?
So actually there's a trick there. The acid, we add 7% sodium chloride there. So its density is twice of seawater. So in the syringe, your acid brine sits in the bottom, there is no mixing. Okay, so when the syringe pushes up, it pushes the sample into the reactor, and there are also some acid in the reactor already. And so it actually, the acid cleans the whole system. So it's like a minute. So the whole process take about 12 minutes to finish, 11 to 12 minutes to finish one analysis. And we repeat 3 times, so it take like about 36 for 3 repeats.
Okay. Our next speaker is Andrew Dixon from the Scripps Institution of Oceanography, and it looks like he's ready to go. Everybody welcome Andrew.
Thank you. Thank you very much, Rolf, and thank you for the invitation to participate in this meeting. For this talk, basically, I'm really asking the question to what extent our CO2 and seawater reference materials have been shown to be potentially useful for C13. And I think it just adds to things that it seems both Wei Jun said just now and others may have said yesterday. So at this point, let me make sure I'm on the right. Okay. We're saying we make these to be reference materials with the ideas that reference materials are homogeneous, stable substances for which particular properties have been established sufficiently well to calibrate chemical analyzers or to validate a measurement process. And so that's the real goal of these as reference materials. And our aim is to make batches of substance for which we know the properties and for which we know that the bottle to bottle of the properties are really very, very similar. My lab at Scripps has been supported by the National Science Foundation now for just over 30 years. And during this time, we've done about 199 separate batches of our reference material, which we've been calibrating since about 1990 for total dissolved inorganic carbon, and since about 1996 for total alkalinity. It took us a little longer to establish a suitable method for that, whereas the total dissolved inorganic carbon method was one that had already been working in Professor David Keeling's lab at Scripps. Not everything was perfect. At least 6 of these batches were unstable, perhaps contamination with a mercury-tolerant organism, and one seemed to have that we had a lot of bottles where the alkalinity changed from bottle to bottle, and we were attributing that to interaction with the bottle, but the reality is we don't have enough test information to be certain of either of these suspicions because we wanted to go on and make more reference materials. We've increased our rate of production over the years. In 2019, we bottled about over 11,000 of the bottles. And typically we've been distributing for the last few years pre-pandemic about 10,000 bottles a year. But we've also distributed smaller numbers, a calibrated alkalinity titrant, buffers for the total pH scale, and seawater CO2 samples whose composition had been modified so as to change away from our more typical reference material so that they could be used for proficiency studies. So how do we even make these? Well, many of you might have seen our 500 ml bottle of seawater, and you get a lovely photograph there. Basically, we take seawater from coastal California. It used to be taken about 100 kilometers offshore, maybe a little more. And then as we started to use more and more seawater, we have moved now that we take it from the input to our institutional seawater system directly by the pier at Scripps. We filter the seawater we collect into a particular clean, large container that will hold, many hundreds of liters. We poison it to stabilize the CO2 contents by adding a mercuric chloride solution. And then we mix it by pumping it around for 2 to 3 days, typically, sometimes a little bit less, depending on how much of a hurry we're in to get things done. And at the end of that, we have a seawater that's been partially equilibrated with the atmosphere, but almost never is its PCO2 equivalent to the local PCO2. So we estimate what the headspace is, and we measure the initial temperature. And as we fill bottles, which takes hours, the temperature in the room changes, plus probably the PCO2 level in the room changes because people are breathing while they're doing the filling. And we adjust for this by saying, okay, if the temperature changed a little bit, let's say 1 degree centigrade, then traditionally you'd think of that as changing the PCO2 by about 4.2%. So let's change the composition of the headspace with respect to PCO2 by about 4.2%, so as to limit how much CO2 transfers between our samples and the headspace, or the other way around, i.e. to keep the homogeneity of CO2 pretty well constant across the batch. And then as these come off, they're sealed. As you can look at that bottle, it's a greased ground glass seal. We put a label on and we put them away and start our process of doing a calibration. Now, some of the data I'm going to show you is from, or mention to you, is from earlier batches where in fact we never did that headspace correction part, but we didn't actually use every drop of the batch either, because we were only making batches of maybe about 300 or 400 bottles, not about 1,200. And so the data I mentioned didn't have headspace control. Most recently, we have done this headspace control. So how do we even calibrate these for total carbon? Well, the basic approach can sort of be viewed here. We've got this so-called pipette filling system where we have a volume of seawater contained between two stopcocks. And it's filled by pressing down on seawater in a bottle, so it goes up, flows through that sample pipette into the overflow reservoir. When the pipette's completely full, we close the stopcocks, take it off here, completely dry out the region outside the stopcocks by a tedious combination of putting in absorbents like, carefully wrapped Kim wipe or something like that, and also by pumping on it on a vacuum line. So now we have essentially a mass of seawater because we had the empty weight of the pipette, and we now have the full weight of the pipette. And that mass of seawater is transferred into a reaction vessel that's part of a vacuum line where we can add acid to it in such a way that it flows carefully through that sample pipette, making sure that everything is washed down into the reaction vessel. And at a certain point, we go, okay, we're now generating a headspace gas here that's largely all the previous gases that were in that seawater, including the evolved CO2. Those gases are then extracted along this vacuum line, first through a crude trap at kind of carbon dioxide, a sort of, I think it's a cold temperature with carbon dioxide there to try and freeze out water vapor, and then a larger trap in that it has a lot more surface area, where again, this central piece can be filled with liquid nitrogen, and pretty well everything freezes out in this trap coming through. Subsequently, so this trap now has mostly CO2, some water that got through trap 1. It's then moved on into these later traps where we can change the ambient temperature by exchanging dewars on the outside, and we can separate the water from the carbon dioxide. And we can view the quality of what's going on by seeing how quickly things are pumping down in that background line. And eventually, the purified CO2, which is done kind of back and forth between these a couple of times, ends up in a tube of glass, which is subsequently flamed off. So we have a flame off tube, finally, that contains, we believe, all the CO2 that was originally in this mass of seawater. And that flame off tube is then used basically to measure in a manometer. This elaborate old-fashioned looking picture is the original Keeling mercury manometer, which we did use for our first X batches. As I said, we're at 199 now, planning to do batch 200 perhaps next week, perhaps a couple of weeks after that. And so, as I said, it's a weighed sample of seawater. It's acidified under vacuum. The CO2 is condensed out. CO2 and water are separated by sublimation. The CO2 is then transferred to a manometer, in this one, it's harder to see, but basically you're looking at a controlled volume inside a glass container where mercury comes up from the bottom to seal off the container volume. And you can go, okay, what's the temperature of that? Well, this large cupboard that it's in is essentially an air bath controlling the temperature. And the pressure inside that container is measured by basically a differential height of mercury using this kind of traveling microscope system to measure the height of mercury. And then you've now got temperature, volume, temperature, pressure, and you're calculating how many moles of CO2 you had using some virial equation of state. So we're now back to moles of CO2 from grams of seawater. So batches 1 to 47 use that one. That's been retired. It's now essentially the museum piece that it looks like. The typical measurement precision on our batches during that time is a little bit bigger than 1 micromole per kilogram. We then switched over to an electronic manometer system, which was more convenient to use and improved the precision a little bit to where it was really just maybe marginally under 1 micromole per kilogram. And we used that for about another 20 odd batches. During this time, the Keeling group had been developing a newer electronic manometer, particularly for this purpose. And the technician that still works for me had been working to make sure it was really well understood how it was calibrated and the precision was improved. So if we look at more recent data, and it's quite a lot of more recent data in the last 12 years, we've probably done over 900 certification measurements on multiple batches. As I said, I think these set of data went up to batch 192. And over about 100 batches, we've done, as I said, about 900 odd measurements. We do typically about 9 measurements a batch. But from this, you can pull standard deviations, and our standard deviation for this is 0.77 with 808 degrees of freedom. So a fairly meaningful understanding of what that term has. It has some content to it. So the goal here, as I said, was to make sure we really got everything. So let's examine some of this, how could we use it for a C13? Well, we did some work back in the 1990s, and we've not really done much since. So preliminary examination said, okay, well, if you took all the CO2 and you could then put it all in an isotope ratio mass spectrometer, then surely you could get a decent isotope value. That was the basic idea underlying the concept. And Dave Keeling's lab had been doing this particularly for taking CO2 samples out of air flasks and some CO2 samples out of water flasks in the past. And as I said, this really was based on the confidence that the extraction efficiency for our seawater was close to 100%. I described in gory detail the extraction method, and looking at those pressures, you actually get a very clear idea on whether or not you have a problem during a particular extraction. Obviously, if there's a slight leak, you bring in extra CO2 from the laboratory. If there's a much more typically than you lose CO2. But we also checked it by making a purified sample of sodium carbonate using a standard analytical approach to preparing this from recrystallizing sodium bicarbonate and heating it to dryness and storing it very carefully. And we could put in weighed amounts directly into this reaction vessel before adding acid or liquid. And then we just put CO2-free water in and add the acid. And this showed quite clearly that we were very close to 100%. We were typically within about 0.05 of that 100% number. And during that time period, forgive me, I have no idea quite what I did to myself there, but it's probably not ideal. Let's go back and share the screen again, believing I won't be redrawing it as I do it. So 3 separate batches of reference material were used. And analyzed for their isotopic composition in the laboratory of Professor Martin Vahlen at Scripps. I think the work was done by one of Dave Keeling's staff, but it was done on a mass spectrometer that had been maintained by Martin Vahlen. And so for each of these 3 batches, with the number of measurements being made on each batch being between 7 and 9, the estimated measurement standard deviation for each batch was of the order of 0.01. As I recall, the highest was probably about 0.011. One was a little, and the other 2 were a little bit below 0.01. And so this was very encouraging that this was really useful. And I know this was an approach that the Keeling group then said, okay, we're going to actually take a lot of these bottles and extract CO2 from a lot of these bottles and use these as a working standard when we're doing oceanic measurements. Because as this had come from California seawater, you get the same comment that was made by Wei Jun, that the numbers obtained on the normal C13 calibration scale were approximately what you'd be expected, not so far from 0. So many years go by, and then Doug Wallace asked me, do I know anything about the isotope composition of our inorganic standards? And I say, well, yes, back in the good old days, which at that time would have been about 25 years earlier, probably, I said it looked really very good. And so he purchased on behalf of his student, Cheng Lin, a group of these reference materials from one particular batch of the water, and they decided to set up this international intercomparison that Wei Jun mentioned, where basically they collected also Atlantic water samples from a particular depth region where it's believed that the water is really very homogeneous, and distributed the seawater samples and our reference materials to all the participating laboratories as though both were unknowns. The left-hand picture shows the data that came, where the black symbols are their measurements on that.
Andrew, you're still on your old slides.
My apologies. So
Yeah.
the black symbols here were the measurements made on reference materials. And the blue were the measurements made on deep seawater samples. More than one particular batch. They took separate batches and bottled them and distributed them. They were close in composition, but not absolutely identical. And these were distributed. And so you can see that there was a strong correlation between the measurement on the reference material and the measurement on the deep seawater sample. And they say, well, okay, if we just took the average value you see here for the black and call that a consensus value for what the C13 levels would be on the reference material, then we could in principle adjust the seawater data. And if you did that, you get the right-hand picture, the magenta, which shows that the scatter has been meaningfully diminished. The plus and minus little band is simply the plus minus 0.05 part per mil goal that is specified by the Global Ocean Observing System as being desirable for useful consistency in such C13 measurements. So undoubtedly, you're a lot closer to that, but not everybody hits that number all the time. So possible simple future for using C13 reference materials in seawater. And here I'm basically talking how we could go quickly from where we stand today to where you might wish to head towards. You could use our already available CO2 and seawater reference materials as a potential basis for such a reference material. As noted by Rolf earlier, of course, and by Regina, these are a natural seawater, and so their actual delta C13 is right there around 0. We produce a lot of them, and they do have low bottle-to-bottle variability with respect to total carbon, and C13 certainly as good as the methods that have been used to look at multiple bottles later. So typically we extract, as I said, CO2 from about 9 bottles, and after we've done the manometry with it, because of the way the system is built, we can actually take that that CO2 back out of the manometer and into another flame-off tube. And we've shown that if you then later put it back into the manometer again, you can't tell it's a different amount of CO2. So if you do it 10 or 12 times, you can see the CO2 diminishing with time. So to do this, the C13 community would need to, say, purchase a bunch of bottles from a single batch, and then you need to decide how you're going to use them. And of course, you could do this for a number of separate batches, but as noted, although our batch-to-batch C13 levels are similar, reflecting the boring nature of the water we take, they are not identical. And believing they are identical would be ill-advised. So early activities you could do. Well, you could extract some CO2 from a subset of these bottles, e.g. at NOSAMS, and measure its C13 levels. And you could even compare those data with some of our extracted CO2 for which you also measured the C13, and see that the two similar but different extraction techniques end up with the same C13. And you could use that information to say, oh, so everything here on batch 203, C13 is about minus 0.042, just making up a number. So now you've got a bunch of bottles where you believe that they're probably very similar one to another, and you know the C13. And you can then use these for test materials for an interlaboratory study, calibrated materials for improving consistency of oceanic measurements, or something that's not really been done is to say, okay, we did this in January. Is it still exactly the same 2 years later? And make sure that you understand better the shelf life of making such materials where it's done for C13. We've looked at this shelf life, particularly for alkalinity, which is a much easier measurement to make than total carbon. And alkalinity, it stays really pretty good for years. Total carbon, we have far fewer data, and we think it stays pretty good for about 3 years. But it may be adequate longer than that. We don't know. And the C13 and the C total carbon are not changing equivalent to one another during the lifetime of a bottle. It depends on the process involved. So possible futures. Well, we're currently funded by the US National Science Foundation until 2024. If you are seeing my video, you will recognize that in addition to having done this for 30 years, I have other years behind me as well. And so it's likely that I myself will retire. And so what then happens to CO2, seawater reference materials, is still an active area of discussion. And possibilities are that we continue at Scripps, with manufacturer certification distribution. Or we move part or all of the process to a new US location or locations. One suggestion that you may hear some from Regina Eastley, Dr. Regina Eastley, is that NIST may become involved in the calibration of such reference materials, perhaps broadly in the form of what are known as NIST traceable reference materials. Either way, if you're still getting seawater samples that are well calibrated or are stable, and we show that they're stable, you could use them in the way that I previously did. It's also possible that Scripps will, I was talking with Ralph Keeling, Professor Ralph Keeling at Scripps, and they have a real interest, growing interest in ensuring that they are doing such C13 measurements, ideally with a new laser-based device, a more extravagant version, I guess, of the one that Wei Jun mentioned, with the hope that they could probably be running things at better than 0.02 in delta C13. But either way, it should be practical to accommodate the needs of the oceanic C13 community once those are clear. I say oceanic because of this comment about if these are all based on a natural seawater, they're all going to be boringly like natural seawater. And contaminating them to be different is a whole separate exercise. So what do you need to figure out? First, you need to figure out what you really need for an uncertainty in C13 to ensure, and the goal is not as great as can do. It really is, have we got particular scientific goals where we can say we can't achieve those goals if we don't have this level of uncertainty? That's a little bit different from how many of us marine scientists normally do this, where we basically say, we'll do the measurement as well as we can, where as well as we can is often biased by the staff available, the comment that Wei Jun pointed out for his Go Ship 13.5 data, the instrumentation available, and the time and trouble available. If you take a lot more work, you can often make it better, but that makes any individual single measurement a lot more expensive. So you need as a community to decide whether the need is for a single oceanic material, which is what I've talked about because that's where I have experience, or whether the costs of preparing alternate compositions can be justified. I'm sure it can be done. I'm less sure that the price is necessarily right. That is, that the improved data uncertain, the shrinking of the data uncertainty is really appropriate to the cost involved. And if you're going to ever set this up properly, you need to figure out how much you need to produce, because this is a slow process to get going. And so even if we said, oh, this is great, let's get going tomorrow, it's almost certainly going to be well into next year before you were even partly on your way. And so the final part, ensuring that the resources are available to supply the planned reference materials, where planned is the number and the quality, reliably. You may need to charge the users for reference materials. That's one way we recoup some of the costs in my laboratory. And we didn't start that way. We were fortunate enough to have large enough grants at the very beginning and small enough number of reference materials that we were giving them away free to start with, but that soon stopped. And our own experience is that as you change the costs, you do affect quite how keen people are to use them. And so that feeds back, because of course, if you make a lot, the unit cost is cheaper, which is why the length of time for which it's stable is relevant. So there's a lot of bits and pieces to think about here. And it's important, I feel, to seek the community consensus to identify what's needed. And I'm assuming that's partially the goal of the discussions at this meeting. But I point out again, whilst recognizing explicitly the costs of any choices made, because the costs are real and they do scale with the number of individual choices and to some extent with which choices. And then the images basically point out that anything I'm saying today depends an awful lot on my having met Dave Keeling at the right time and that extensive funding from the National Science Foundation. Thank you.
Thank you, Andrew. I especially enjoyed the last few slides where you essentially set the stage for the discussions we're going to be having later today. I wrote down what the essential criteria are, and I hope we can focus on what the community's needs are in our later discussions. Does anybody have a pressing question right now? We're running ever so slightly behind schedule. Let's
I
go
had
for-
one hopefully quick question, Andrew. This is Rick Wonenkoff. So my understanding, I think it's great what you mentioned, but didn't emphasize that you've got extensive material experience with certifying these reference materials for alkalinity and DIC, and I think a lot of lessons learned can be forwarded. So currently, when you so what you are recommending is, as I understand it, it's probably not a recommendation, but sort of suggesting is that you would basically assign a reference value for C13 as one possibility, but have it checked by a different lab. Is this currently done for DIC and TA? Or
No,
are we all? I always assumed that you had the right value.
That's actually not what I was suggesting, Rick, though it's conceivable. Basically, my suggestion was that if you used our reference materials, a lab could be tasked with assigning the C13. My own lab might move into doing that, but our timescale and your timescale might not match. I think we're talking years, not months. The other part is the comment you make about separate labs doing it. And the approach we've taken for the alkalinity and the total carbon is to try to use and to test what one might think of as reference methods, where the numbers we get do not depend upon the availability of particular chemical calibrants. So for the total carbon that I outlined, how do we know the volume, the pressure, the temperature? The temperature is measured with a thermometer. Calibration of thermometers is an understood art. The pressure is measured with the manometer. The manometer can be confirmed and tested because we have a high quality dead weight tester system that we can connect directly to the manometer and confirm the calibration. The weak link is the volume. And the volume is actually done by, we fill a vial with pure CO2. The vial is in a water bath when this happens to control its temperature. We know the volume because the vial is sealed with a stopcock, and we can calibrate that volume by weighing water in that container repeatedly. We control the pressure we fill it at by using that same dead weight tester to make sure we put a known amount of CO2, known pressure of CO2 into the vial when it's closed. If that CO2 is then transferred to the manometer, and we now measure at our volume level marker, the pressure and temperature, we can infer exactly what the volume was from knowing how much CO2 was in. And we have a variety of vials of somewhat different sizes that allows us to have confidence in the numbers that we get that way. So nothing there required a real measurement of total carbon anywhere to define our number. And that's the basis we've used. It would be great to have another lab that had a somewhat different way of coming up with their initial calibration do that as a comparison. It has not happened. For isotopes, there's a lot of work in ratios, and the closer measuring the difference between two things that are very close together in delta C13 is a well-practiced art, let's put it that way. But actually saying that you necessarily understand what the C12, C13 ratio is much more limited and possibly not key for the ocean science that we talk about. But the difference is that that's the benefit of having multiple laboratories checking. They're basically saying there are ways we know this can be screwed up. If we got the same number in two different labs because we're using roughly the same method, then likely it's the number we wanted. In our approaches, we're basically saying, let's try to get a method that we could tell if we screwed it up. And if we don't screw it up, it's pretty well the right number within some potentially understandable uncertainty. And that's the approach we've taken. So it's rather different.
Thank you, Andrew. You essentially headed off a number of discussion points that we have for later. I feel like I hope you can stick around. Our next speaker is, I hope I'm pronouncing your name correctly, it's Dr. Regina Eastley from NIST, National Institutes for Standards and Technology.
That's correct. I share my screen. Are you able to see my presentation?
Yes, your audio is very quiet, Regina.
Oh, it is. Okay. Is this any better?
A little bit.
Okay. I'm not sure why, but I want to thank the organizers for this opportunity. It has been really enlightening for us to be here for the past couple of days. We actually have 4 Nist staff members that are here, myself, Rebecca Kraft, Jason Waters, and Michael Winchester, who is our group leader. And so today I wanted to talk about the Nist Traceable Reference Material Program as a potential model for seawater reference materials, and really in relationship to the isotope values that are needed for this community. So NIST, we are the National Metrology Lab for the US. And one example is that we have some really long-term reference material programs. One of those is in the area of pH standards. So we've had over 76 years of experience in doing pH measurements. And I think one thing that's different about our program versus Andrew's program is that typically for our reference materials, when we standardize a batch, we typically try to ensure that the batch lasts for about 10 years. So this is true for our pH reference material programs. If you were to look at our annual sales, for example, for one of our pH SRMs versus the high volume of production in the Dixon lab, Dixon absolutely dwarfs us in comparison. We typically sell about 86 units of a pH SRM per year versus his 10,000. So this problem is not unique. It was actually faced by the gas metrology community years back. And in that case, the vast need for reference materials really exceeded NIST's capability of producing the materials. And so in this case, a NIST traceable reference material program was started back in the 1990s. So the way that it works is that commercial specialty gas companies produce high volumes of gas cylinders, and then a select number of those cylinders actually comes to NIST, where we do the certification. The specialty gas companies, they maintain the lot, and they are responsible for the distribution and the sales of that material. So we have recently proposed this idea as a potential way of doing something similar with seawater reference materials. And so the idea is that on the Nist side, we will provide measurement services. So for example, doing measurements of alkalinity titrations, dissolved inorganic carbon, other non-certified measurements that might be needed for those materials. And for this community, we are also willing to do isotope value assignments like Delta C13. We haven't really talked about Delta O18. I don't know if that's needed, but we also have capabilities of doing that. And then we could also perform stability assessments. With our measurement services, we work very closely with the Nist Statistical Engineering Department and our Office of Reference Materials. And so those two departments, they help us to basically design our experimental designs to ensure that they are solid, to establish our uncertainty budgets, and the Office of Reference Materials helps to provide certificates for each of the batches. And if there is a need to refine any type of certification, then we work with them as well to change those needs. So the major limitation that we have is that we don't actually have access to seawater. And so this is where we propose that if there were different bottling facilities around the country, perhaps on the West Coast, obviously, clearly we have the capability of doing that on the West Coast, but maybe an East Coast source or Gulf of Mexico source, for example, if we had facilities that could provide bottled samples, those facilities could perform batch acceptance testing as well as bottling, homogeneity assessments, and they would be responsible for the distribution. So similar to the Nist Traceable Reference Material Program in the gas metrology realm, those facilities would send bottles to Nist where we could do the measurements. The other limitation that we have right now is that we don't have capabilities of doing carbon-14 measurements. So this is where an expert collaborator or collaborators would be assigned to help us with these measurements. In terms of a projected timeline, we anticipate that in order to do these measurements or for the existing CO2 standards and for new isotopic values, we project that providing titrants like the HCl titrants and total alkalinity values will take the shortest amount of time. This is something that we're absolutely considering, and we actually project that we could do that within 2 to 3 years. For dissolved inorganic carbon, we are estimating that bringing that capability will take between 5 to 7 years, and this is the same thing for the Delta C13. We, as if you've come to the meeting this week, you've noted that we do have a isotope ratio mass spectrometer, which is purchased. Right now, we are doing some lab renovations to completely bring that system online. So the dissolved inorganic carbon and Delta C13 ratios are definitely possible, and they could be tested within a few years. We also have been in contact with our gas metrology group. So with our gas metrology group, they actually have been working on the CO2 measurements and comparisons between our facilities here and the NOAA labs to help improve the carbon dioxide scales. So there was actually a recent WMO round robin where they demonstrated that the Nist and the NOAA value assignments for total CO2 are exceptionally close. They've been getting closer over the years. And so I know for these measurements, they actually used a Picaro to do some of the measurements for total CO2, as well as a GCFID. I don't actually have the slides for that, but I think that's kind of a nice tie-in, especially to Wai-Jun's talk earlier. So we are actively working in this area to help improve our capabilities and our ability to measure materials. And like I said, as for C14, we can't do that measurement directly. And so in that area, we would need an expert collaborator to help provide values for materials. And this is something that we've done for other reference materials. One thing that I wanted to highlight is that in addition to our regular standard reference materials and reference material programs, we also offer research grade test materials. And what these are is there are specialized batches of materials that have a known homogeneity or sufficient homogeneity, and they are tested for stability. These are often used for interlaboratory studies. They are assigned a particular number to be distributed. And this one that I have is just an example of a test material that was put together to help provide standardization, most recently for the SARS-CoV-2 testing. And so these are RNA fragments. There was funding that was provided from the outside in order to support the development of this material. And so it was distributed to labs that needed it without a particular cost because it was funded by, I think, some of the stimulus money. So these materials, they're not highly characterized, but because they're used for interlaboratory studies over time, our knowledge of the materials as well as the value assignment for those materials can improve. They don't actually have to be traceable to the SI, but in time, as we learn more about the materials, let's say if they were used for interlaboratory studies, they could actually lead to higher order reference materials. And so this is a new kind of format that we're using to help get test materials online faster. In terms of a funding model, one thing that we're thinking about is that Nist is definitely committed into this area. And so Nist will contribute funds to provide not only equipment, but salaries to staff. In order to do this type of research, we would likely need to hire more another individual or a few individuals to help with the efforts. Additionally, we could receive funding from NOAA through like an interagency agreement in order to help support this. We can't directly receive money from NSF. So the idea too is that if there are additional studies that need to be done, and if there are academic labs or groups of labs that are interested in this work, NSF would likely be a very good source for funding that could help contribute knowledge in this area. So that's, initial investments to help fund equipment, facilities, and personnel. In terms of the sustainability of the program, we know that from our Nist traceable reference material programs that the commercial manufacturers, since they are the ones that are actually selling and distributing the materials, they do bring in funds from that are generated by the sales. Presumably, if the reference material provider has funds from maybe NSF and also from those reference material sales, a portion of those funds could go to Nist to help kind of continue our operation and our participation in the certification process. This is how our gas metrology program actually works. So the specialty gas providers, they actually pay Nist just through invoicing a fee to conduct the measurements that are required for the certification. And just like Andrew noted in his presentation, there are a lot of questions and things that we think about when we are considering the production of a new reference material. So I think some of this information we have gathered from the discussions that we have, and I know that we'll cover more of these today with the panel discussion, but things that we think about are, what is an appropriate unit size? What type of packaging would be needed? What values do you need on the material with targeted uncertainties? And how many do you anticipate would sell per year? Like how many customers are out there? And there is a question about the lifetime of material and, what is a tolerable price point for these materials? So that's all that I have for today, just to kind of give you a quick overview of what we have been thinking about. And so this is a list of some of the contacts Michael Winchester is the inorganic chemical metrology group leader. Jason Waters and I, we both have been working in the area of inorganic carbon for a while. And Rebecca Kraft is a little bit new to the oceanographic community, but she is our IRMS specialist, and she is here at the meeting as well. So we welcome your questions.
Regina, thank you very much. Both presentations were awesome in that they really got down to what we need to be figuring out. And maybe we can't figure it all out today, but they get down to some real questions about what we need to. Basically, we have people who are willing to help us out, and we just need to know specifically what we're going to ask for. At this point, are there any questions for Dr. Eastley at NIST? Apparently not. So we had planned to transition directly into a discussion of what intercomparisons might still need to be performed. Given that we've just left the topic, or we're still on the topic of reference materials, I'd like to propose, I'd like to kind of override my co-conveners and propose that we launch right into the panel discussion of reference materials. Anne or Bob or Roberta can shout me down if they wish.
I think that's a fine idea. So I'm with you.
Anne, do you mind introducing the sort of the panel / roundtable format?
I actually not quite sure how a panel works on Zoom.
Okay.
But certainly the members of the panel should reveal themselves with, turn their cameras back on. And the people we have here are Liz Canuel from NSF. You can raise your hand when I introduce you. Roberta Hansman from NOSAMS, Regina Eastley from Nist, Andrew Dixon from Scripps, Bob Key from Princeton, and Maxi Castrillejo from in between ETH and Imperial College. Did I get everyone? And to make it more familiar, if you're asking a question, why don't you, I'll lead. If you're speaking, why don't you reveal your face so that people can, the panel people can see you. I guess one of my questions is I really don't know. So a question I have is, there's a need for a reference material in the isotope community for sure, but there's also a need for working standards. Do people use your CRM as a working standard, like a secondary standard in their laboratories, or is it sort of a primary standard?
We distribute it as a reference material, which gives you the flexibility of how you choose to use it. In the initial stages, I strongly encouraged people to use it as a check that the number they got with their system, with their calibration, matched what should be expected, with the prejudice that our number was indeed the one that should be expected. Very rarely has that been done. In many cases, labs use ours as a material they analyze regularly and tweak their data, making the simple concept that any changes from time to time in the number they got on our material is indicative of a drift in their measurement procedure, which may or may not be true. And, I think that, so both are used. More typically, it is used as a calibration, but it's often used as a fairly frequent calibration check from which drift corrections are also made. And I would wonder at the statistical integrity of any understanding of the ultimate uncertainty of such measurements. And I think our community has a problem, which is that we are addicted to low precision without necessarily a concern for low uncertainty.
Yeah, I would second what Andrew just said, with maybe the tweak that there was some uncertainty in what, Andrew, you could chime in on this, but I would say the first 2 or 3, maybe 4 years that the CRMs were being produced, the carbon community, which was much larger in the early 90s than it is now, would report an average or any drift, or basically they would report all of the results that they got running a series of CRM over the length of a cruise, typically at the rate of 1 or sometimes 2 per day. And they would publish the, assuming they didn't have any drift, then they would simply publish the average and the difference between their number for the CRM and what Andrew had, had published for his value for that CRM. But as he said, once, especially when we started assembling the Pacific data set, it became so incredibly obvious that the CRM were a better way to calibrate than what the various labs were using, that all of the carbon groups started just exactly what Andrew said, adjusting to the CRM. And that is done through today, with the exception that now the at-sea alkalinity and total CO2 techniques over 30 years, the bugs have been reduced to the point that, 1, the bugs have been reduced, and 2, the number of groups making the measurements on the long lines cruises has been reduced even more. The bottom line being that frequently the shipboard determination measurement of the CRMs is within 1 or 2 micromoles of what the published value is for that CRM. And in those instances, there may be times when people do not adjust, because it's the assumption is that you're just as likely to make an error doing the adjustment as you are leaving the data alone. Hopefully this is always recorded, at least in the cruise report, and ideally it's in the header of the file, although I know that that's gotten to be much less over the years, but made a huge difference.
In the context of what Bob just said, I would point out that in those early days, he's quite right, but there were about 6 groups in the US who were making oceanic carbon measurements, and possibly another 6 groups in the world who were making oceanic carbon measurements. And we were distributing materials to all of them. In 2019, we sent materials to 110 labs. So the open ocean users are a small proportion of the total users, though still a very significant proportion of the total usage.
Yes, agreed.
So that,
We've only got 2 labs in the, no, 3 if you count the group out at Hawaii, but it's AOML, PMEL, and the group at Hawaii for the US now.
so that actually brings up something I was thinking about, which is the funding model. And many of the people who are interested in the open ocean isotope standards are not US people. How do NSF and Nist feel about producing, well, Nist obviously produces standards for the whole world. So but how does NSF feel about paying a lab to produce a standard that will be used internationally?
Well, I'll just comment my own personal experience on this, is that they have been glad to do it because of the fact that many of the projects that are involved with CO2 benefit substantially from an international distribution of data. And so the US projects benefit from the other data being of an equally well understood quality. And that, I think, has been accepted by every program manager I have dealt with at NSF, which is very few over the years. Neil Anderson originally, through to Hetty Edmonds more recently.
Well, and also on the international side of that, when we started combining the data sets into not GLODAP version 1, but the subsequent versions, Carina, Pacifica, and then GLODAP 2, the foreign scientists or non-US scientists just became painfully aware that it was a really good thing to do to start using those, and subsequently all of the major labs in Western Europe, Japan, Australia, Korea, and that would be the main. It's also, I don't know about South Africa, but they're all on board with using the Andrews.
We send
reference
materials to all those places, probably
Yeah.
about 27 different countries we send material to.
Yep.
I think at
So Liz, do you
Calibrate-
have anything? Liz, you're the NSF representative, so I thought it might be useful to hear from you.
Well, I think Andrew answered the question very well. I mean, having, when we have good measurements across the international community, that serves the field as well as the US science programs well. And anyway, Andrew actually I've only been on board for a few weeks, so Andrew has a lot more experience over
But
the
you've been there
years.
before. You've been there before too. so.
Yeah. But,
Couldn't one adopt a model wherein if you are from an NSF or NOAA lab that is contributing to this effort, your cost per reference material is, I don't know, $80. Whereas if you're not from one of those programs, your cost is $200.
yeah.
Of course,
I
you
think
you could. There are two parts to that. Number one, it's more complex to administer in that my university, essentially, the costs are justified not because you can afford it or you deserve it, but rather because this is a definable reimbursement towards the project that can subsequently be audited and defended. The next part is the cost per bottle is amortized over the number that we distribute. So if we put out 2,000 bottles or less, as we did in 2020, we lose a huge amount of money. If we put out 10,000 bottles, we were breaking even because of the salaries and equipment thing, particularly salaries. So if you end up changing quite who uses this, and you change the prices, but you also likely change this ambition for a community understanding of data quality.
Andrew, are you back to normal or relatively normal production of the
This
CRM?
year, we have produced a number of batches with over 1,000 bottles each. Our next batch is scheduled to be the first one that will be produced in a style approximating how it was done in 2019.
Great.
But at the moment, getting bottles to put the water in is our limiting step. We have many on back order from manufacturers, presumably tied up in the world's logistic problems.
Andrew?
And I wanted to say something really quickly to everyone, not just the panelists. Both of our speakers this morning identified that we need to be getting clear about how many, well, first of all, what our target value ought to be, how many samples or what our target uncertainty needs to be, and start thinking about how many reference materials we might in our labs use per year, because we need to sort of get a guesstimate of what the throughput needs to be. So if people want to, while we're sort of we're not haggling, while we're discussing, if people want to put that in the chat, that would be really great. If you just take a guess as an initial discussion point. Thanks. There are some folks with their hands up. I'll step out now.
Yeah, I guess I had a question about this cost thing. Hey, it's Adam from Hui. It seems like if you were to add the delta C13 of DIC as a routine measurement on the, Andrew, your current process, that would obviously add a cost that is associated with that CRM that, obviously not everyone who's buying your CRM wants or needs to know that value. And maybe that's an argument for someone in our kind of subset community running your CRM in lab, like NOSAMS or someone. And then that being a community, at this point at least, a community resource rather than a paid service that's provided that then has to be shared across every single bottle of CRM that's distributed. Or maybe that's the reason why it makes more sense to do it that way, because the cost gets spread out so much. Yeah.
You're exactly right, but the complexity is that we're producing 11,000 bottles per year because people are using 10,000 bottles per year for sure, which means that any one batch, which is only about 1,200 bottles, disappears in months. So that was why I had the suggestion that as a community, C13 think, at least initially, in just buying a piece of one of those batches of a sensible amount for what they needed, and then they could then distribute it for years. Because if you want batch 157 to compare with the data that Wei Jun was talking about, no can do. Long gone. Every bottle. So please send me bottles. I need them. I need them. I need them. We go, well, we're making them as fast as we can. And so that's the problem, that the turnover we have for the other parameters is so much faster than the predictable turnover for C13, that keeping them somewhat separate probably has at least a benefit until C13 is so obviously a more straightforward measurement, perhaps using systems like Wei Jun was pointing out, that a larger community is doing it and feels reassured by availability of a reference material that is widely accepted.
Yeah, I'll just say that I use a Picaro-based system too. So I'm going through my CRMs at a rate at which I'm measuring DIC, not at the rate at which I'm measuring delta C13 of DIC. And I'm assuming that Wei Jun and probably others on this call are doing the same thing. But to your point, maybe then it makes more sense to think about a really standardized procedure for normalizing to known carbonate standards rather than trying to assign a value to a distributed seawater standard.
Yeah, I mean, this comes down to the degree to which your uncertainty is the extraction process or the measurement process. With the liquid seawater-based one, you get both together. And you get, which is really what you need to know for the data you're providing as a scientific commodity. And finessing that by doing it differently has to be recognized, what you gain and what you lose.
So maybe one option would be for, say, every 10 batches, you have one of them or two of them have the delta C13 value. So that will probably reduce the cost of get that assigned.
But you also therefore needed to take that batch, put it separately from the other batches that have been distributed to everybody else.
Yeah.
And therefore fit into your program of producing a way of papering over that gap where you suddenly took a whole bunch out of circulation.
I see.
So yes, it can be done, but no, it is not immediately trivial in current circumstance.
I want to interrupt for a sec. Maxi Castrillejo has had his hand up for a little while.
Yeah, so I have three questions. One is for NOSAMS and Andrew, perhaps, whether you tried to measure radiocarbon in your CRMs to check for the variability between bottles and so on. I guess from what we have seen of delta C13, it would be fine for C14 to do maybe to use few batches as Wei Jun Kai is suggesting. Then
So I can address that first question.
yeah.
When we first, I mean, it's a historical issue, but yes, so C14 should be measured on the, as well as C13 and C14. The reason we didn't jump on, we wanted to do this from the start, and the reason we didn't jump on it was, for some unfortunate reason, the one batch we got from Andrew was carbon-14 hot. So I got scared early on, and but it certainly, well, for the future, Roberta should be speaking. So.
Yeah, I just wanted to say, Kalina presented some data. We did have one of the reference materials from Andrew and only measured C13. We haven't measured C14, but it would be easily done, of course. And we would expect the stability to be better than C13. Yeah.
Thanks a lot. And then, so I have two questions more. One is for Nist. It was unclear to me to provide the C14 value. I guess you would need to send the water to different AMS labs and then get a kind of a consensus value or something like that. Would that be the idea?
Yes, that's the idea. We actually do that for other reference materials. If we don't have the capabilities here, we'll have expert collaborators that will do the measurements, and Nist actually does the value assignment with the data that they provide.
All right, and then the last question is regarding funding. I feel that the US, you've been pushing this so many decades, and I wonder, whenever you apply for these SNF applications, can you include PIs from other countries, or this is not accepted? I'm just thinking about ways of helping.
Right. That, in terms of PIs from other countries, I think that is a better question for Mike.
Yeah, so I just turned my camera and microphone on because I anticipated that maybe I should answer that. I don't think it's prohibited. I think we would have to have some offline conversations and talk with NOAA and others, but I don't see why that's a prohibited situation. So I'd be more than happy to talk with you about it. So thank you for that.
That's all.
So Regina, I have another, oh, there, Bob, I should have Bob done. Question for you. You said that Nist would be willing to help fund some of the collection of the material. Does that, so if you know, post Andrew, if Woods Hole Oceanographic were willing to say, okay, we can collect all the water. We have this pipe that brings in 0.2 micron filtered water. We can buy a vat and then start making our own standards. Am I correct that you said Nist might be able to subsidize that? Paying the people who are actually doing the collection and the
Right. I think I had in the slide that we could help with the collection process and then do analysis as well. So I think Mike actually.
You want me to answer?
Yes.
Yeah. So what I have in my mind is, as the guy that pushes the dollars around for the group, is that I've said this in other OCB meetings regarding the broader effort for carbon seawater standards, is that I think I can find in my budget probably a couple $100K a year to subsidize what I'm thinking really is our internal cost, because we could send it out the door also, but I mean, the total bill is the total bill, whether it is Nist cost and scripts or whoever on the outside, there's a sum total that this would cost. And some of that is cost to Nist to, to pay people like Regina. And so I'm thinking that, we can probably, well, I'm committing that we can help offset our own cost. And I think that's why, Regina, in your slide, you had it set up that NSF, just as not to put NSF on the hook here or anything like that, but, just the same way that NSF has been funding Andrew for 30 years, maybe that funding, just as a suggestion, could go to the distributor, whoever that is, the producer and distributor. Is that clear?
I think as clear as it can be right now, and it's all, but thank you.
Yeah. And sorry, I'm trying to turn my video back off, but I can't for some reason. I don't guess it matters.
I don't want to, this is Rolf Sonnerup. I don't want to interrupt or complicate things, but we have been getting some responses in the chat as to what kind of target values we should be looking at. And there are a number of groups that are interested in more than one target value. That is to say, more than one seawater sample that is at 1 per mil or whatever, but that covers a broader range for somewhat more diverse scientific goals than just the C13 SUS effect. And to help, Jeff Chanton writes that I hope I pronounced that right, to help isolate issues related to extraction versus the analysis itself, it would be useful to have both liquid and I presume sodium bicarbonate forms of reference materials. I hope I represented the folks on the chat correctly. That wasn't a direct question. I was just trying to summarize the community's needs.
Yeah, or little blocks of spar calcite are particularly good, and they're very stable. Sometimes other kinds of carbonates can exchange and misbehave.
Have you got a block of spar calcite that you'd like to I don't know how you cut such a thing.
I have my personal block of spar calcite, but I don't think it would be large enough to supply everybody here, but we could invest in one.
I wondered if you had bought that at an AGU conference.
I think, yeah, I probably did at that little gift shop, that they have all the fossils and things.
I see that Bob Key has had his hand up for a while. So.
Thanks, Ann. I had a few questions for Andrew, and this is after having listened to Andrew's long talk and then the short summary of it today, and having been involved in the program for forever. One is, and I may have gotten the answer to this just a minute ago. I was wondering how many samples from each batch you tend to archive. First question.
We
And that-
archive very few.
That's
Because of it's possibly, if I look around the lab now, I can find some batches where I've got 20 and some batches where I've got 1.
But 20 and 1. Okay, so that would be enough to do limited time series tests on the aging. If we make 2 assumptions, one, that we can ignore the analysis cost for the isotopes, and 2, that it increased the total number of samples, total number of reference materials you were producing by 20%. Would you hazard a guess as to what the cost per CRM would be? A lot of the people here on this on the call today have never bought CRM from you, and I think are probably unaware of what those costs are. And for that matter, it's been forever since I bought any, so I'm not up to date on that either.
So presently, we charge the 2019 charge that we were charging, which is $33 for the content of the bottle. You were also asked for $20 for the possession of the bottle. If you return the bottle to us for recycling and reuse, then that $20 is available for you to purchase against the bottle charge for a later reference material purchase, should we still be in business at that time.
Okay.
This is not a way to say, aha, University of California owes me $2,300. The university is very clear about that.
Okay.
And
so
that number is going to go up. So currently it's about $53 a bottle. If you just buy a couple of bottles and you don't worry about whether you're going to send them back because it's too much trouble to send them back, it's costing you $53 a bottle. That cost is going to go up in part to cover losses occurred for salaries during the pandemic.
All right. But I expect your large users do tend to return the bottles. Maybe the small
The
ones
large
don't
users
because of the
do
shipping.
tend to do it.
Yeah.
But on a schedule that suits them rather than us. So we always have to carry a surplus to smooth that out. And that's where we're hitting problems at the moment.
Right. Yeah, we've run into that with the C14 lab as well over the decades, but getting low on bottles or having too many, whichever was the case.
Would that price come down by increasing the number per year by 20%?
Right.
Likely not, because as I said, prices are going up largely because the individuals doing the work remain the same individuals and their salaries go up both for coverage of any inflation, but also for recognition of continued merit. If we kept swapping in cheap people, we could keep prices down, but it might not be as reliable.
Right. Well, if everything was ideal, could you handle a 20% increase in production? And let's take 2022 or 2023 is the year. Could you up production by 20%?
I doubt it.
Okay.
In that our current container from which we collect samples is pretty well filled to the top when we do a batch. And we take it down to where the level of the water is level with the hole we're taking the water out of.
Okay. You empty it without tilting.
Yeah, we empty it without tilting. And so we put in a bit over 800 liters and we take out about 700 liters is really what it is.
And well, you would then have to increase 20% in the number of runs you made. And,
yeah, we would have to have extra batches in a year. And in actual fact, our time constant on it takes a certain amount of time to clean the apparatus completely, because without that, we end up growing an organism that is mercury tolerant that can contaminate the batch, which is not a good thing, because then the idea that they're stable goes to hell. And that cleaning process takes about a week. Getting everything ready for a batch takes about a week. Washing all the bottles for a batch takes about 3 weeks. The fastest we've been really doing these reliably has been 5 or 6 weeks between batches. We'd have to squeeze that a little closer to get an extra 20% with the same equipment. And so all those things have to be better managed, including distributions of vacations and illnesses.
Right. I guess the last question I had is, now I know you're not going to add an AMS, but would you be interested in attempting to provide the reference number for C13, or are you not interested in attempting that?
I spoke,
and there by you, I mean at Scripps.
I spoke yesterday with Rolf Keeling,
Mm-hmm.
and he is interested in doing that, provided he can acquire resources that allow him to do it. And he's working in part for some of his programs with money from the Schmidt Foundation, and or one of the Schmidt Foundations, and it may be that. But his real interest is using this Aerodyne system for C13 analysis and replacing his isotope ratio machine. So
Andrew?
yes, he's interested, and Scripps, I think, there might well be interested, but it's going to be one of these things that changes depending upon external pressures, where external pressures are community interest and financial availability of the resources.
Yes, and presumably, if you assume the responsibility for making and distributing these, the C14 would have to be done somewhere else.
C14, as for NIST, would be something that would absolutely require.
Yeah, I mean, a priori, I would whatever.
I mean, in principle, I guess, because we do some C14 from Scripps with the group at Livermore, but that's definitely a stretch compared to current experience and intentions.
Yeah.
Could I ask, just related to that? Sorry, and sorry if I missed it. Andrew, for each batch, is gas that you extract for quantification and then could then be sealed off and measured isotopes later, how many per batch of those do you have?
9,
Or do you,
approximately 9.
Okay, thank you.
I do have a question too, like if, like when you proceed to purchase a batch, can we save some of those samples so we can test our capabilities here at Nist to do those C13 measurements? I put in the chat that our gas metrology group is actually working on an Aerodyne method. So that might be an interesting comparison.
So I mean, as we say, we have 9 extracted CO2 samples from any one batch. A batch originally started out with 1,200 bottles, so a subset of that could conceivably be put aside as the liquids themselves, requiring later extraction, and whatever process is being used to make the measurements. But the difficulty with that is, as I said, you A, have to get them aside, and you B, have to buy them at that time so that we're not compromising the costs being spread around everything else.
Andrew, I have a question. You said recently you started to put a headspace, with the CO2 similar to the PCO2 in the water. I guess that will benefit stability of DIC bottle from bottle during the bottling process, right? You create a larger and larger headspace for that purpose. But
yes, it does. And it also benefits when we have in the past made modified seawaters where we added some bicarbonate,
okay,
and we added CO2 so that we changed the alkalinity and the total carbon to make
my question is, if that headspace is not fully equilibrated with the water, from beginning, then you could possibly change delta C13. That will be, right, add an uncertainty there.
The answer is yes, that's certainly true. But let me suggest why I don't think that's probably your first big problem. We have a batch we did recently where we completely screwed up. Our headspace control system was clearly wrong. We probably had a very high PCO2 headspace. You cannot see it in our batch until bottle 1100. And then after bottle 1100 out of our 1240, you see total CO2 going up, and we took a bunch. When we saw that, we went back to the actual bottles and looked, and you see pH going up in a very smooth and clean pattern while alkaline D stays constant. So clearly, when we've got a very low total volume still in the container and we're doing that equilibration, it's quite noticeable. But I don't think that's typically the case, though it could be, because the reality is, as you know, the average equilibration time for PCO2 is meaningfully quicker than ensuring you have an isotopic equilibration in a volume of water.
I see. Yeah, I agree. Still, it's
and even then, my point is, it's clearly not very fast. Otherwise, we'd have seen the data, the problem earlier in the batch.
Thanks.
This is probably a popular interruption. It's lunchtime. I wanted to ask if there's anybody out there who hasn't asked a question yet who would like to make themselves heard. It sounds like people are expressing themselves through the chat or are hearing what they're needing to hear. At 12:35, we are going to reconvene and we're going to separate into breakout groups oriented around the specific needs of the communities, C13 of Ocean DIC, C14 of Ocean DIC, and then a breakout group for the freshwater, groundwater groups. One of the things I wouldn't mind people thinking about, this is what I'll think about over lunch, is exactly what sort of targets are we looking at? What del C13 value are we looking for? And what range of values we need? I think we should also start thinking about just how many standards we could use. It's tempting to write a proposal and buy an entire batch from Dixon's lab and go from there. But it would be nice to be a little more specific than that. Okay, that's all I got to say.
Could I just make one final comment that I didn't mention, Rolf, which does come up?
You may.
Weijian's equipment showed him using gas-tight bags as a way of dispensing small amounts of a liquid that he believed probably didn't change from the beginning of the bag to the end of the bag. We,
Right,
as you
it's the
saw in the
same bag.
picture, use glass 500 ml nominal capacity bottles with about 560 milliliters of seawater in each bottle. Realistically, if this is also to progress, recognizing the influence of packaging and perhaps even establishing a way to do that packaging for preparing a reference material may help the C13 as much as it helps the community generally, because we spend a lot of money is spent shipping a lot of mass of glass around the world and then back to my lab to get washed and used again. And so going to a very different packaging would be good, but the hazard with the different packaging is it would be a shame to start doing it in bulk before you know it works.
So that's okay. One more variable. We'll see y'all in about half